Have you ever stopped to think about how a formula, a really old one, like over 2,000 years old, could solve a super modern puzzle? Well, it turns out one of the most famous equations in all of history is the key to measuring things that seem completely, totally out of reach. All right, let's dive in. So, we're going to start our journey at the absolute peak of modern engineering. Why? Because we're going to uncover a secret that's been hiding in plain sight, a secret that connects a massive skyscraper today directly to the ancient world of math.
It sounds like a pretty straightforward question, doesn't it? But the answer has to account for the actual curvature of the Earth, some huge distances, and a little bit of geometric magic. This is the mystery we're going to solve together.
To get started, we need a few key details. We're not at the very, very top, but we're on the observation deck, which is a mind-boggling 1,450 feet up in the air. Now, you're going to want to remember that number. It's absolutely crucial for later. Okay, so to find our answer, we can't just, use a giant tape measure. We need a tool that can handle these massive distances and invisible lines of sight. We need to unlock a kind of secret code that's hidden inside a really simple shape. And that shape? It's the humble right triangle. I know, it might seem really basic, but its properties are so powerful, they form the foundation for pretty much everything, from building your house to mapping the stars. So let's just make sure we're all on the same page. A right triangle has two sides called legs. We can call them A and B, and they meet to form that perfect 90-degree corner. The third, longest side, the one opposite that right angle, that's the star of the show, the hypotenuse, or C. And this brings us to the secret code itself, the Pythagorean Theorem. You've probably heard it, a squared plus b squared equals c squared. It's just a fundamental truth about every single right triangle that exists. If you know how long the two legs are, you can always figure out the length of the hypotenuse. And you know what? It works perfectly every time. Let's take the classic example. Say one leg is 3 units long and the other is 4. Okay, so you square them, you get 9 and 16. Add those together and you've got 25. And the square root of 25 is 5. That means the hypotenuse has to be 5. It's just that simple and so powerful. But what if you already know the lengths of all 3 sides and you just want to check if it's really a right triangle? Well, it turns out we can just flip the formula right on its head. This lets us use the theorem not to find a side, but to prove a shape. This is what's known as the converse of the Pythagorean theorem. See, the original theorem starts with a right triangle and helps you find a side. But the converse starts with 3 sides and proves if it's a right triangle. If a squared plus b squared still equals c squared, then bingo, you've got one. It's like a detective tool. Let's try it out. Imagine you've got a triangle with sides 5, 12, and 13. Is it a right triangle? Well, let's square the 2 shorter sides. 5 squared is 25. 12 squared is 144. Add them up, you get 169. And what's 13 squared? Well, it's also 169. The numbers match up perfectly. So, yep, that is absolutely a right triangle. Okay, so we've pretty much mastered the ancient code. We now have the exact tool we need to head back to Dubai and finally solve our skyscraper mystery. And this is where it gets really, really cool. Check this out. Our line of sight to the horizon, a line from the center of the Earth out to that horizon point, and a third line from the Earth's center all the way up to us in the tower, they form a gigantic, planet-sized right triangle. The right angle is right there at the horizon. So let's label our giant triangle's sides. Leg A is the Earth's radius, which is about 3960 miles. Leg B, that's the one we're trying to find, the distance to the horizon. And the hypotenuse, C, is the Earth's radius times the height of the observation deck. But hang on a sec, we've got a little problem. Our units are mixed up. We have miles and feet. We've got to fix that. So we need to convert the tower's height into miles. Turns out 1,450 feet is about 0.27 miles. So our hypotenuse C is just 3960 plus 0.27, which gives us 3960.27 miles. Easy enough. Now we can finally plug everything into our formula. We've got 3960 squared plus d squared, that's our unknown distance, equals 3960.2 squared. And just like that, we have everything we need to solve for d. And when you run the numbers, there it is, 46.64 miles. From the observation deck of the Burj Khalifa, you can see almost 47 miles to the horizon. An ancient formula just measured the curve of our planet from the top of a modern skyscraper. How amazing is that? So, we solved our modern puzzle. But this whole way of thinking, of seeing these hidden triangles all around us to measure things that seem unmeasurable, that is anything but new. In fact, it's a timeless idea that connects our skyscraper right back to the ancient world. The key to how they did it back then is a related concept called similar triangles. Basically, these are triangles that have the exact same angles, so they're the same shape, just different sizes. Think of a photograph and a bigger copy of it. The secret is that because they're proportional, the ratio between their sides is always the same.
And this is where things get truly mind-blowing. On the right, you see our modern problem, but on the left, that's an ancient one. The triangle formed by a person and their shadow is similar to the giant triangle formed by a pyramid and its shadow. Same shape, just way different sizes.
Over 2,500 years ago, the philosopher Thales used this exact principle. He literally just measured his own height, the length of his shadow, and the length of the pyramid's shadow, and with just that information, he could calculate the height of the Great Pyramid without ever leaving the ground. Same logic, just a few thousand years apart. So that leaves us with this final thought. This simple little triangle gave us a language to describe and measure our world, connecting ancient pyramids to modern cityscapes. And it really makes you wonder, what other elegant, powerful truths are hiding out there in plain sight, just waiting for us to find the right way to look?